we will start it. Okay, thank you, Rico. I would like to ask God help to open the class with the opening prayer.
Sure, Dr. Lucia. I'll start. A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Allahumma sholli ala sayyidina Muhammad wa ala ali sayyidina Muhammad. Allahumma ighfir lana dhunubana wa liwalidina warhamhuma kama rabbayana shighara. Rabbi ishrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Rabbi zidni ilma warzuqni fahma. Amin.
So much, Rizka. Okay, before we proceed to the class, we will take pictures as usual. Nabila, can you help?
Yes, I can help, Dr. Lucia.
Everybody, please open your camera.
Okay, I'm going to take a picture. Which is 1, 2, 3.
Is it done?
It's okay. Once more, please. 1, 1, 2, 3.
Không được dân được cái này thì
It's done, Dr. Lucia.
Thank you very much, Nabila.
Thank you, Dr. Lucia.
So I will share my screen. Can you see my screen, Nabila? Can you
Yes,
see
I
my
can.
screen?
Yes,
Thank
I
you.
can.
Okay, so today, Dr. Mark, we will go back to module A1 again. So students, last week we have discussed about module A1. We have shown you how to calculate every problem 1 and 2 that we have performed. But based on our last year's evaluation, students do not really get into this module. Meanwhile, this module is the basis for the next module. That's why we decide to take more time exploring this module. So today we are going to explore, we are going to analyze the results that we have tabulated last week. Okay, so jadi berdasarkan pengalaman tahun lalu, mahasiswa tidak menggunakan waktu yang banyak untuk mengeksplor apa-apa saja yang ada di dalam modul A1 ini. Padahal modul A1 ini akan menjadi dasar untuk pengerjaan modul-modul selanjutnya. Nah, oleh karena itu, kami memutuskan untuk memberikan kalian waktu lebih banyak untuk mengeksplor modul A1 ini. Nah, minggu lalu kita sudah mempraktekkan bagaimana melakukan kalkulasi untuk soal nomor 1 dan 2. Minggu ini kita akan membahas hasilnya. Ya, we will start with the first question. You know the first question already, so I will move directly to my spreadsheet. Okay. So, since there are 3 atoms, C, N, and O, I am going to discuss only one of them, which is oxygen. Okay, so this is the atom, which is oxygen. The method, we have 6 methods. As before, method 1 is HF and the basis set STO3G and so on. Method 1, 2, 3 is Hartree-Fock. Meanwhile, method 4, 5, 6 is DFT. We calculate the singlet state, the energy of the singlet state, the energy of the triplet state, and we will find the energy difference between the singlet and the triplet state. Okay, so here is the difference. We have tabulated this in the previous week. So I will show you directly the result here. This is the result that we obtained from the output file of our calculation. the unit is in Hartree, but here for the difference between the triplet and the singlet state, the
Sorry,
energy
Dr.
converted.
Lucia. We can't see your screen, your Excel spreadsheet.
Oh,
Yes,
sorry. Oh, I'm sorry.
we are still on the module.
Yeah, okay.
Right, thank you.
Thank you, Dr. Mark. So
Right.
here is the spreadsheet that I have provided. This is the same as what we have did in the previous week. So this is the tabulation for our calculation results. The first column A is the atom. We have to tabulate for 3 atoms, carbon, nitrogen, and oxygen. But here I show you only for oxygen atom. In column B, we have the method. The method is from 1 up to 6. Method 1 to 3 is using Hartree-Fock. Meanwhile, method 4, 5, 6 is using DFT. The exchange correlation is P3LYP. Here, our tabulation is the energy of the singlet state. The unit is in Hartree. This is what we get last time. And this is the energy of the triplet state. The unit is in Hartree. This is the result we obtained last time also. Now, in column D is the difference between the energy of the triplet state and the singlet state. But I have converted the difference into electron volt by times the result with 27.2116. So this is what we obtained. We have done this before, so I believe all of you have these results already. So this is the result that we get. However, from this tabulation, from the results that we obtained so far, there are more things to do, to explore based on these results. The first thing, I wrote it here for the analysis. The first thing that we can do is to compare the results from all methods. Method 1 up to 6. When we compare the result in column E from all the 6 methods, we can see that all methods agree that the triplet state is more stable than the singlet state. We get this result from the difference between the triplet and the singlet state. Since the result is minus, it means the triplet state should be lower than the energy of the singlet state. So the first conclusion that we can make is all methods agree that the triplet state is more stable than the singlet state. Hal pertama yang bisa kita lakukan dari hasil yang kita dapatkan, nah di sini delta, yang kita dapatkan adalah delta. Nah, semua hasilnya negatif. Itu artinya energi di keadaan triplet lebih rendah daripada energi di keadaan singlet. Jadi kalau kita bandingkan hasil dari metode 1 sampai dengan 6, kita bisa katakan semua metode setuju bahwa keadaan triplet itu lebih stabil daripada keadaan singlet karena energinya lebih rendah. However, the distance between the two states here refer to the triplet and the singlet states, is the closest in method 6. Method 6 is here. I have provided a simple diagram here for you. Now, if we compare the results for method 1, the difference is around 3.87. So this is the singlet state. This is singlet, and that's also singlet according to method 1 and method 6. This is triplet state, and that's also triplet state. According to method 1, the difference is around 3.87. But according to method 6, the difference is lower. It's around 2.80. So the distance between these two states is the closest in according to method 6. That's the other thing that we can say. Jadi hasil ini menunjukkan bahwa selisih atau jarak antara level energi keadaan singlet dan triplet itu paling dekat menurut metode 6. Kalau kita kalkulasi menggunakan metode 6. Itu poin pertama. The other thing that we can analyze from our results is we can compare the result in column C3, in cell C3 up to C5. C3, C4, and C5. If we compare these three results, we can see that the one that is the most negative is the result according to method 3. So the trend is the energy of singlet according to method 1 is the highest, followed by method 2, and the last is method 3. Here in this comparison, we can see that there is the effect of basis set that we are using. It means if we change the method is the same, which is Hartree-Fock, but if we change the basis set, it means the trend of the energy changes as well. So you can see the trend is 1 it has the highest energy and 3 has the lowest energy. Now we can do the same for this. We use the same method for that. Okay, we can compare column C6 up to C8, and we can draw the same conclusion as before. Method 4 has the highest predicted, the highest energy for singlet state. Meanwhile, method 6 produced the lowest, obtained the lowest electronic energy for singlet state. The other thing we can compare is the result in column D. Here is column D3. We can compare the result in column D3, D4, and D5. D3, D4, and D5. And the result is consistent with the first one. Method 1 obtained the highest energy for the triplet state. Meanwhile, method 3 obtained the lowest energy for the triplet state. The comparison here shows the effect of basis set, the same as before. Because method 1, 2, and 3, they use Hartree-Fock, but the basis set is different. Oke, hasil di poin 3 ini sama dengan, mirip dengan yang ada di poin 1. Kalau yang kita bandingkan adalah hasil dalam kolom yang sama, maka kita bisa menilai apa efek dari basis set. Contohnya, kalau kita bandingkan di kolom C3, hasil di kolom C3 sampai dengan C5 atau D3 sampai dengan D5, kita bisa katakan bahwa kalau kita mengganti basis set, energinya juga berubah. Dan perubahan energinya itu makin rendah, semakin negatif. Artinya semakin stabil keadaan triplet yang didapatkan. Next. Okay, this is the same as before that I have discussed. This is also the same. So we can do much more things to analyze our results. Not only finding the difference between the singlet and the triplet state, but you can explore more about what to say about the results that we have obtained so far.
Sorry, Dr. Lucia.
Yes.
Give me a minute. I'm disconnected to the projector. The students can't view the spreadsheet actually. Give me a minute. We have some technical problem here. Give me a few minutes.
Sure, Doctor.
Atau tak apa kot. Pasal kita ada kelas.
Yang ini tak pernah cabut je ni, yang sebab kita speaker tu.
Lepas tu ni macam mana nak
Cuba cucuk lama. Cucuk ni dekat doktor lama. Begitu.
yang ni dia buka sana. PC ni dia tunjuk. Saya cuba. Ya, saya punya. Boleh. Tak boleh. Okay. Alright. Alright, Dr. Lucia, so sorry to interrupt you. We can continue.
Okay, should I repeat some informations or I just...
I think it's okay. You can continue.
Okay, sure. Thank you. Okay. Jadi ini analisis-analisis yang bisa kita buat. These are the analysis that we can make from the results that we obtained so far. The next thing we can do, we can compare the results that we obtain in cell C3 and C6. C3 is this and C6 is that. C3 is the energy of the singlet state. We obtain this using Hartree-Fock and STO3G. In C6, we use B3LYP and STO3G. As you can see these two results, the energy obtained by Hartree-Fock is higher than the energy obtained by B3LYP. So if we compare these two results, we can compare the effect of the method between Hartree-Fock and DFT. You can also do the same thing for the other cells. For example, C4 and C7. C4 and C7. It means we compare the results from the same basis set but different method, Hartree-Fock and B3LYP. You can also compare the results from cell C5 and C8 to know about the effect of the method. As we can see, the result is consistent. The result that we obtain using DFT is always lower. The energy is always lower than the energy obtained by the Hartree-Fock method. Okay. So these are things that we want you to explore about the results that we have obtained so far. Okay. Is there any question for question 1 before we move on to question 2? How about your student in UTM, Dr. Mark?
Yeah, I just asked them. No response. I think that every one of them are clear now. They understand.
All right. Okay. Thank you, Dr. Mark. How about in ITERA? Okay. Okay. Thank you, Ayu. Okay, let's move on to question 2. Okay. In question 2, I hope you still remember the question. I will open the module again. This is exercise in question 2. We need to perform energy calculation for oxygen atom, but we need to add restricted. And the method that we use is B3LYP 321G. The basis set is 321G. This is method number 5. So that's what we are going to do. We should obtain the total energy and orbital atomic energy. So I will go back to my spreadsheet. Okay. We are using column A is the atom, which is oxygen. Column 2 is the method. We are using method 5, B3LYP, and the basis set is, the exchange correlation is B3LYP, and the basis set is 321G. And we add extra information here. First calculation is without restricted, but the second calculation is with restricted. For the first calculation, 5A, we have done this in question number 1. So we just need to take the results and put it here for the singlet and the triplet. While for the second one with restricted, I have shown you how to do it last time. So we have the results already. I directly put the result in here. And then from the results that we obtain, we find the difference between the triplet and the singlet state. So this is the result that we obtain without the restricted information in our input file. The difference that we obtain is minus 2.87. But if we include restricted in our calculation, the energy, the difference in energy changes a little bit. It becomes minus 2.85. So if we compare both results, we can see that we can conclude that the distance between the two states, the singlet and the triplet state, is the closest when we use the restricted in our calculation. So if we use restricted, the energy changes. It changes the distance between the singlet and the triplet state. So at first, without the restricted, it's like this far, this big. And when we use restricted, it changes a bit. So that's the first result that we obtain. And then we can also, if we compare the result in column, in cell D3 and D4, we can see that the result is exactly the same for the singlet energy of the singlet state, either without restricted or with restricted. It is exactly the same. But with the triplet state, the energy with restricted is higher than the energy we obtain without the restricted. So without restricted, the energy is lower than with restricted. That's the second conclusion that we can make. And the third, we are going to check for the orbital. So I will show you how we are going to compare the molecular orbital, the atomic orbital. So I will go to the Gauss view again from here. Okay. So we are going to compare the atomic orbital of oxygen atom in its singlet state. First, we are going to compare these two results. In singlet state, without and with restricted. We start with the singlet state first. Okay, I open two results of my calculation here. First one in the left is the results from oxygen atom using method 5 in its singlet state without the restricted area, the restricted information. Meanwhile, in the right side, I use the restricted information in the input file. Let's check and compare the atomic orbital of both results. Okay, I will start with the first. I will place it there. And this is the second. Okay. As you can see, we have obtained the same value of energy before, and the atomic orbital is also exactly the same. The energy in each orbital. This is the first orbital. It is filled with 2 electrons. The first orbital is 1s, 1s2. For oxygen, the first one is 1s2. So orbital s, but it is filled with 2 electrons. Let's take a look at the shape of the s orbital. I will show you how to visualize the s orbital. We go to this part, new Gaussian molecular orbitals. So we will take the information, we will extract the information about molecular orbital from our CHK file. We obtain this file when we perform our calculation. So we load the result from there. Done. Now we are going to visualize this number 1, 2, 3, 4, and 5. I will enlarge it so you can see. I will start from the first. This is 1s orbital. It is filled with 2 electrons. This is the shape of orbital. If I move it around, the shape is the same in all directions. Now, this is 2s. As you can see, the orbital gets larger compared to the first one. It is filled with the 2 electrons as well. I go back to the first one, okay? This is the shape of the first one. As I move around, the shape is the same. It's like a sphere. This is the shape of the second orbital, orbital 2s, I meant. Okay, it is the same in all directions. It's also like a sphere, but the volume is bigger. Now let's move on to the third.
Sorry, Dr. Lucia, can you give me a
Yes.
minute because I'm still struggling to generate the orbitals, the molecular orbitals.
Sorry, can you repeat, Dr. May?
They're trying to generate the molecular orbitals.
Oh, I see. Okay.
Yeah.
Yeah.
Can you maybe show them one more time?
Sure, sure.
Yeah, sure.
Okay, I will repeat again. We'll close this. Okay. Okay. I will visualize the one without restricted. Okay. I will go to this part. This is what I obtained. Go to new Gaussian molecular orbitals. Here we have our checkpoint file. Make sure that you take the data from the correct CHK file. So this is oxygen using method 5 in its singlet state. So this is the CHK file. Let's load the file because we are going to extract the data about the molecular orbitals from this file. Silakan bisa sambil mencoba juga ya, yang di ITERA dan di UNSUD bisa sambil mencoba juga. Jadi kita memanggil informasi tentang molekular orbital dari file CHK. File CHK ini kita hasilkan ketika kita melakukan kalkulasi. Jadi ketika kita melakukan kalkulasi, ada input file. Yang pertama yang kita running. Setelah kita running, kita akan dapatkan dua file. Yang pertama log file. Log file itu adalah output kalkulasi kita. Dan yang kedua adalah CHK. Nah, CHK ini berisi data mentah. Nah, salah satunya data mentah yang ingin kita gunakan dari file CHK adalah informasi tentang molekular orbital. Nah, pastikan kita memanggil file CHK yang benar, and then we click load. Okay. Okay. After that, go to visualize. Because we are going to visualize the molecular orbital that we have extracted before. Go to visualize and choose the atomic orbital that you are going to visualize. In this case, I'm going to visualize number 1, 2, 3, and 4. I can exclude number 5. You can just click it to choose or not to choose it. Yang di ITERA bisa mengikuti? Oke, yang di Unsud bagaimana? Oke. I will wait for a little bit more.
Kamu boleh tak ada? Tengok yang S orbital, P orbital. Normally we say the next is px, 2px plus 3y. If it doesn't matter, let's get 3d. If that's x, then the other one is 1. The x, then the other one. Okay. It doesn't matter, they are all 3. So, the first load, please visualize, and highlight.
Once again, make sure you try and know how to do it because this will be the basis for the next module.
If we know the T is for X, Y, or Z, which direction? Only right click on the canvas. Ready? View. Is if you ask your purpose, baru EY tadi. Ya, berarti itu teknik satu yang ini. This is 1x, 2x, 3x, 3y. Itu kata standard in action, then the other one will be exit that. So you can see which one to do.
Should we continue, Dr. Mark?
Yes, sure.
Okay.
I think they are fine now. Okay.
Okay. So after you choose which one to visualize, and then click update. I will enlarge this. First, we can visualize the first orbital. This is 1s orbital. It has 2 electrons inside. This is the 1s, the shape of 1s orbital. Our oxygen atom is in the middle. Next is 2s orbital. As you can see, 2s orbital is bigger than 1s orbital. Next, I move to 2p orbital. This is 2p orbital, but I will also show the Cartesian axis so we know in which direction this orbital is. This is our Cartesian coordinate. This is x-axis, y-axis, and z-axis. It means this p orbital is headed toward the z-axis. That's why we call it pz orbital, and it has 2 electrons inside. Next, this is also pz. I'm sorry, this is also p orbital, but the direction is toward y-axis. So we call it py. So in number 3, before we have 2px orbital, 2pz orbital. And in number 4, we have 2py orbital. Both has 2 electrons inside. So that's the visualization for oxygen atom in singlet state, but without restricted information in our input file. Next, I will move. Sorry. Next, I will move to the other result using restricted keyword. We do the same as before. We visualize it. And of course, you can see that it's the same as the previous one. It is exactly the same. So the atomic orbital that we obtain for oxygen in its singlet state, either with restricted or unrestricted, if we don't use restricted, the Gaussian will still treat it as restricted calculation. That's why the result is the same for both cases. Now, I will move on to the result for the triplet state. Jadi hasil untuk kalkulasi orbital energi orbital atomik untuk kasus oksigen singlet itu sama, baik ketika kita tidak menggunakan restricted ataupun ketika kita menggunakan restricted, karena Gaussian akan memperlakukan keduanya secara sama, meski kita tidak menggunakan informasi restricted di input file kita. Sekarang saya pindah ke kalkulasi atom oksigen di triplet state. I have 2 results, the same as before. This is triplet without restricted information, and this is triplet with restricted. I will compare both results. This is the first one. And this is the other one. Of course, you have noticed that the result is different. When we use in the left side is without restricted. When we don't use restricted, the result, the Gaussian obtain the result in the alpha and beta molecular orbital. But if we use restricted, we will have only one result like this. So you can see. You can visualize it the same as before. So you can visualize this and also that using the way that I've shown you before. But I will go directly to the conclusion. So up to now, we have seen that in the singlet state, the molecular orbital is the same. Either we use restricted or not without restricted in our input file, because Gaussian will treat the the one without restricted the same as the restricted calculation. But for the triplet state, if we don't use restricted information, we will get two types of molecular orbitals, the alpha molecular orbitals and the beta molecular orbitals. This type of molecular orbitals has no physical meaning. It has no physical meaning, so we cannot extract the physical information from this type of orbital, because as you can see, the electron in the first orbital, which is in 1s supposed to have 2 electrons. But according to unrestricted calculation, these 2 electrons are placed in 2 different rooms. They are not combined into one room, but they are placed into 2 different rooms, while we know they're supposed to be in one same room. The correct calculation, the correct result is given by the calculation using the restricted information. As you can see, in the restricted calculation, the two electrons occupy one same room. So they are in the same room. Kalau tanpa restricted, kedua elektron orbital S diisi oleh 2 buah elektron. Tapi 2 buah elektron itu ditempatkan di 2 ruangan yang berbeda. Yang satu di ruangan sini, yang satunya lagi di ruangan yang sana. Kalau kita pakai restricted, kedua elektron tadi dipaksa untuk berada di dalam satu ruangan yang sama. Nah, ini hasilnya. Mereka berdua berada di dalam satu ruangan yang sama. Sama juga dengan hasil di level energi selanjutnya. Ini artinya hasil molekular atomic orbital untuk kalkulasi tanpa restricted tidak punya artifisis. Tapi kalau kita menggunakan restricted, dia memberikan artifisis untuk kita. Okay, that's the end for second question. We will move to question 3 if there is no question from you for question 2.
Hi, Dr. Lucia. Yeah, I have a question. What about the electronic energy? Which one should we follow? The restricted or the unrestricted one?
Okay. Okay, for the electronic energy, we have compared it before. We get 2 results. The one that we obtain without the restricted, the difference is lower than the one that we obtain with the restricted information. The energy is higher. The energy that we can use is the one without restricted. So if we want to use the electronic energy, we choose the electronic energy from the calculation without restricted. But if we are going to analyze the atomic orbital, then we will use the result from the restricted calculation.
But my other question is, if there is no physical meaning in the unrestricted calculation, can we still use the electronic energy from the unrestricted one?
Yes. The energy has the physical meaning. So the difference is that the one that has no physical meaning is the molecular orbital.
Okay.
The atomic orbital. So, for the one that use restricted, we know that when we apply restricted, it means that we force the electron to stay in one same room. So we force them to be together. Meanwhile, they want to be separated. So it means the energy of the system will be higher because we force them to be together in one same room. So for electronic energy, the one with physical meaning is the one that we obtain from unrestricted calculation. But for the atomic orbital, we can choose to use the information from the restricted calculation. Jadi untuk energi elektronik yang bisa kita pakai adalah energi elektronik yang dihasilkan dari kalkulasi yang unrestricted. Tapi kalau kita mau menganalisis molekular orbital, maka kita harus melakukan kalkulasi yang restricted. Karena kalkulasi yang restricted itu yang memberikan informasi atomic orbital yang benar. Karena seharusnya 2 elektron itu berada di dalam satu orbital yang sama. Jadi ketika kita melakukan kalkulasi restricted, kita paksa 2 elektron itu untuk tinggal di dalam satu ruangan yang sama. Okay, should we move to the third question, Dr. Mark?
Yes, sure. Is there any other questions from UTM? No? Are there? Okay. Can continue. Question 3.
Okay. From ITERA, how about? Okay. Unsud? Okay. Let's move on to question number 3. Okay. In question number 3, I will open the question again. We perform energy calculation for atom hydrogen and helium in ground state using the 6 method, and we tabulate the result. We compare the result to the experimental result. Okay, so I believe you have done with the calculation. We start with the hydrogen atom. Here is the 6 method that we are using. This is the total electronic energy, but the unit is still in Hartree. I use doublet state for this. The spin multiplicity is doublet. And then I convert the energy into electron volt in column D. And now this is the experimental results. How do I get this experimental result? Now I will move to the textbook that we use to obtain the experimental result. Okay, the title of the textbook is Handbook of Chemistry and Physics. And then I will go to the contents. We will go directly to section 10. And the one that we will check is ionization energy of atoms and atomic ion. Okay, so this is the page, ionization energies of atoms and atomic ions. So as you can see, in the first column is the value of Z. This is the second column is the element starting from hydrogen and so on. The third column marked with 1. This is the energy needed to kick out 1 electron from the atom. The energy is called ionization energy. So for the case of hydrogen atom, since it has only 1 electron, if we want to take out that 1 electron, that means we have to use this amount of energy, 13.598443 electron volt. The unit is in electron volt. Hydrogen has only 1 electron. For the case of helium has 2 electrons. So if we want to take the first electron out, the energy is around 24.58. But after taking one electron out, and if we want to take the second electron out as well, we will need a higher energy than that. It is around 54.41. It means that when both electrons are stay together inside helium, they kind of don't like each other. So that if we want to take one out, it's quite easy to kick one of the electron out. But after the first one out, the second electron feels happy because he or she, the electron is alone inside the helium. That's why the energy to kick the second electron out is larger, since the second electron likes to stay inside the helium. And the total energy that we need, if we sum up the energy to kick out the first electron and the second electron, we will obtain the total electronic energy of the system. The value here is positive, but if I move to the spreadsheet, I will use the negative value because it has different meaning. This is positive because this is the energy, the amount of energy that we have to give to kick out the electron. But in our tabulation here, I will use negative because it means this is the energy that is needed for electron to interact with the nucleus. So I write negative in here, negative 13.6 in here for hydrogen, and negative 79.01. This is the summation of 24.58 and 54.41. Okay. So this is our experimental result, and we have to compare both the result from our calculation and experiment. And this is the difference that we obtained. As you can see, from all the methods, method 6 is the most accurate. It means the difference with the experiment is the smallest. The conclusion is also true for helium atom. Method 6 predicted the most accurate value because the result is the closest to the experimental value. Besides comparing the result between among all the methods, you can also do as what I have shown you before. We can also compare the result only from C, for example, C3 up to C5 to see the basis set of effect. Or the result from C6 to C8 to see the effect of basis set. You can also compare the result in cell C3 and C6 if you want to know the effect of the method and so on. Okay, so that's the conclusion for the third question. Okay, maybe you can take a look again at your results to make sure that we get the same results for this calculation.
Right. Maybe we'll give them a few minutes just to look at their own results. And if they have any questions, they can ask us.
Yes, sure. Thank you, Dr. Mark.
Right. Thank you.
Oke. Bagaimana, Bu Lucia? Sudah bisa masuk sesi saya?
Iya, Dokter Febian, kita sudah bisa melanjutkan.
Baik.